Okay, so let's see my disease cure research assistant, which hopefully will help people cure diseases, like help researchers come up with cures for all sorts of diseases, including cancer, which I have a more specialized cancer cure research assistant for. But let's show you how to get to that. So you go to ChatGPT, you can go to either the app or the website, and then you go to let's see, what was it? So you go to explore GPTs on the drop down menu. Then you want to search for disease cure research assistant. I can also include a link down below in the video here. Actually, there it is. So I'll go through the default prompts here and show you what it does. I can actually have it read it out for you too. See how far. Okay. So it's finished now. Let's read it out here.
Recent research in diabetes has shown promising advancements toward potential cures for both type 1 and type 2 diabetes. 1. Inceptor blocking drugs. Scientists have identified a new drug target known as the Inceptor receptor.
Hmm.
Blocking this receptor on pancreatic beta cells can enhance insulin sensitivity and beta cell function. This method is particularly promising for addressing the detrimental effects of diet induced obesity and enhancing beta cell health in individuals with prediabetes and type 2 diabetes. Sixth source. 2. Stem cell therapy. Researchers at the University of Alberta are developing a method to genetically engineer a patient's blood cells to revert into stem cells, which are then reprogrammed to become insulin producing islet cells. These cells are transplanted into the patient's liver, potentially eliminating the need for lifelong immunosuppressive drugs and addressing the shortage of donor islets. 7 source. 3. Oral insulin formulation. A new nanotherapeutic formulation of insulin has been developed, allowing for oral administration instead of injections. This formulation aims to reduce episodes of hypoglycemia, making diabetes management easier and less invasive for patients. 8 source. 4. Study, the Diabetes Remission Clinical Trial, DIRECT, has demonstrated that a structured weight management program can lead to significant remission rates in type 2 diabetes. The study found that continued support and weight loss maintenance are crucial for sustained remission, highlighting the importance of lifestyle interventions alongside medical treatments. 9 source. These findings reflect a multifaceted approach to diabetes treatment, combining pharmaceutical, genetic, and lifestyle strategies to move closer to a cure. Further research and clinical trials are essential to refine these methods and make them widely accessible.
Okay, so let's look at one of these sources here. Okay, that's pretty cool. So now I guess I want to see if any of you guys are researchers here would like to get your feedback on this. So let's go ahead and try one of the other default prompts here. Okay, let's read this aloud here.
Proposing new cures for AIDS, acquired immunodeficiency syndrome, involves exploring innovative therapeutic strategies that can either eradicate the HIV virus or achieve long term remission without antiretroviral therapy, ART. Below are some potential avenues and their evaluations. 1. Gene editing, CRISPR Cas9. Proposal: use CRISPR Cas9 technology to excise HIV proviral DNA from the host genome, thereby eliminating the virus from infected cells. Evaluation: pros: potential for a complete cure by removing the virus from infected cells. Advances in gene editing have made this approach increasingly precise and efficient. Cons: challenges in delivering the gene editing tools to all infected cells, risks of off target effects causing unintended genetic changes, ethical and regulatory hurdles need to be addressed before clinical application. Hummer 2. Latency reversing agents, LRAs. Proposal: develop and use LRAs to activate latent HIV reservoirs, making the virus visible to the immune system or susceptible to ART, followed by immune based therapies to clear the reactivated cells. Evaluation: targets the main challenge in curing HIV, the latent reservoir. Could work synergistically with existing ART to achieve a functional cure. Cons: risk of inducing viral replication without effective clearance, leading to a resurgence of infection. Potential for significant side effects if the reactivation affects other cellular processes. 3. Broadly neutralizing antibodies, BNAbs. Administer BNAbs that can target a wide range of HIV strains to suppress viral replication and enhance immune clearance. Evaluation: pros: can be tailored to target diverse HIV variants, may offer prolonged suppression of the virus with fewer side effects compared to daily ART. Cons: high cost and logistical challenges in production and administration, potential for the virus to develop resistance to BNAbs over time. Mana 4. Therapeutic vaccines. Proposal: develop therapeutic vaccines to boost the immune system's ability to control or eradicate HIV, either alone or in combination with other therapies. Evaluation: pros: can provide long term immunity and control over the virus, potential to reduce the need for continuous ART. Cons: difficulty in eliciting a strong and durable immune response against HIV. Vaccine induced immune responses may vary among individuals, impacting effectiveness. Number 5. Proposal: use stem cell transplants from donors with a naturally occurring CCR5 del32 mutation, which confers resistance to HIV infection. Evaluation: pros: proven potential for cure, as demonstrated in the Berlin patient and the London patient. May offer a definitive solution for patients who can undergo the procedure. Cons: highly invasive and risky, suitable primarily for patients with concurrent conditions like leukemia. Limited availability of compatible donors with the CCR5 delta 32 mutation. 6. Combination therapy, kick and kill. Proposal: combine LRAs to expose latent HIV with immune modulators or gene therapies to eliminate infected cells. Evaluation: pros: holistic approach targeting both latent and active virus, potential to significantly reduce the viral reservoir. Cons: complexity in coordinating the timing and dosing of multiple therapeutic agents, increased risk of adverse effects due to multiple interventions. 7. Nanotechnology based drug delivery. Proposal: develop nanoparticle based systems to deliver antiretroviral drugs or gene editing tools directly to infected cells, enhancing efficacy and reducing side effects. Evaluation: pros: targeted delivery could improve the efficiency of drug or gene therapy, potential to lower doses and reduce systemic toxicity. Cons: technological and manufacturing challenges in creating and testing these systems, potential for unforeseen biological interactions, and long term safety concerns. Conclusion: each proposed cure has its unique strengths and challenges. The most promising approaches, such as gene editing and BNAbs, are in advanced stages of research, but still face significant obstacles before they can become widely available. Combination strategies, leveraging the strengths of multiple therapies, may offer the most realistic path toward an effective cure. Ongoing research and clinical trials will be crucial to address the technical, ethical, and safety issues associated with these innovative treatments.
Okay, so that's really cool. Now let's ask it which of these would you recommend following there? So like, that could be multiple or one. I don't know if we can read while it's generating. Probably not. No. Okay. I don't know if I'll have it read these out. So the gene editing, high potential for a cure. Okay, cool. And the VNABs, and combination therapy of kick and kill. Oh, maybe it's. I don't know if it's doing them all. Okay, no, it actually did pick top five, so which would work in combination. So therapeutic vaccines and then nanotechnology based drug delivery. Okay, so that's cool. Hopefully this can help some people here or help guide research a little bit. So let's see. Let's just finish testing the default prompts and you can type your own things. Well, actually, that's to give you an idea of stuff. So, oh, actually, I had an idea about heart disease. So let's try that. So I'm kind of looking for like a discussion of my ideas. So let's do. Not sure. I'll just do that. Like the thing that you put in your blood. Yeah, I actually proposed this on Stack Exchange a while back and stuff, and people actually brought up a good point that pieces of the heart plaque could go dislodge and get stuck elsewhere, I guess, while it's liquefying. So let's see if ChatGPT will pick up on that. Oh yeah, that's a good thing. Actually, I think I will read this out here. So yeah, I'm not like a medical expert or anything, but that was an idea I had a while back that might do a lot of good in the world. So let's have it read it out here.
Developing a drug that can safely liquefy heart plaque without damaging other parts of the body is an intriguing and ambitious goal. This approach would aim to target and dissolve atherosclerotic plaques that build up in the arteries, which can lead to heart attacks and strokes. Here's a structured plan to explore the feasibility of your idea. 1. Understanding atherosclerosis and plaque composition. Plaque composition. Atherosclerotic plaques are complex structures composed of lipids, fats, cholesterol, calcium, and cellular debris. Plaque stability. Some plaques are more prone to rupture, leading to cardiovascular events, while others are more stable. Current treatments. Statins, lifestyle changes, and surgical interventions like angioplasty and stenting are commonly used. Hazard 2. Mechanism of action. Targeted drug delivery. The drug would need to specifically target plaques without affecting healthy tissues. This could involve identifying unique markers or receptors on plaques. Enzymatic degradation. One approach could be using enzymes to break down the components of plaques. For example, certain proteases or lipases could be engineered to specifically degrade plaque components. Selective solubilization. Another method could involve molecules that selectively dissolve the lipids and other components in the plaques. MER3, safety and specificity. Biocompatibility. Ensuring that the drug does not cause harmful effects on healthy tissues is paramount. This involves rigorous testing in vitro, in the lab, and in vivo, in animal models. Controlled release. Developing a system where the drug is released in a controlled manner at the plaque site can minimize systemic exposure. Side effects. Potential side effects need to be thoroughly investigated, including impacts on liver function, blood vessels, and other organs. 904. Research and development. Literature review. Conduct a comprehensive review of existing research on plaque targeting therapies. Look for studies on enzymatic degradation, nanotechnology based delivery systems, and other innovative approaches. Experimental design. Design experiments to test the efficacy and safety of potential compounds. This could involve in vitro studies, using cultured cells and plaque samples to test the drug's effect on plaque components. Animal models. Testing in animal models of atherosclerosis to assess the drug's efficacy and safety in a living organism. Human trials. If preclinical studies are successful, the next step would be clinical trials in humans. Number 5. Potential challenges. Targeting specificity. Achieving precise targeting of plaques without affecting other tissues. Immune response. The body's immune response to the drug or its delivery system. Regulatory approval. Navigating the regulatory pathway for new drugs, which involves demonstrating safety and efficacy through rigorous testing. Next steps. 1. Gather existing research. Identify and review key studies on plaque composition, enzymatic therapies, and targeted drug delivery systems. 2. Collaborate with experts. Engage with cardiologists, biochemists, and pharmacologists to refine your approach and design experiments. 3. Develop a proposal. Outline a detailed research proposal, including objectives, methodology, expected outcomes, and potential pitfalls. 4. Secure funding. Look for funding opportunities from academic institutions, government grants, and private foundations. By taking a methodical approach, you can systematically address the feasibility and safety of developing a drug that liquefies heart plaque. If you need help finding specific research articles or have more detailed questions, please let me know.
So actually, stinks that I didn't. Yeah, it did do really well, but I kind of wish I covered the risk. Like, it did cover side effects, I guess. But let me ask it if it thinks there is a risk about the heart plaque dislodging and causing problems. And one of the thoughts was to put like that net thing in there. Oh, okay, yep. Okay, let's see what happens with this. Let's read that.
Yes, there is a significant risk that pieces of heart plaque could dislodge during treatment, leading to more severe complications such as heart attacks, strokes, or embolisms. This phenomenon is known as plaque rupture or embolization. Here's a more detailed look at the risks and potential strategies to mitigate them. Our risks of plaque dislodgement. 1. Plaque rupture. When a plaque becomes unstable, it can rupture, releasing its contents into the bloodstream. This can lead to the formation of a thrombus, blood clot, which can obstruct blood flow and cause a heart attack or stroke. 2. Embolization. Small fragments of plaque or thrombus can travel through the bloodstream and lodge in smaller arteries, causing blockages elsewhere in the body, emboli, which can lead to tissue damage or organ failure. 3. Inflammatory response. The dislodgement of plaque can trigger an inflammatory response, which can exacerbate cardiovascular conditions and contribute to further plaque formation. Strategies to mitigate risks. 1. Controlled plaque degradation. Gradual dissolution. Develop drugs that gradually dissolve plaques, minimizing the risk of large fragments dislodging. Enzymatic regulation. Use enzymes that break down plaque components in a controlled manner, ensuring a slow and steady degradation process. 2. Targeted drug delivery. Nanoparticles. Utilize nanoparticle based delivery systems that can precisely target plaques and release the drug locally, reducing systemic exposure and unintended effects on other tissues. Site specific activation. Design drugs that are activated only in the presence of specific enzymes or conditions found within plaques. 3. Stabilizing agents. Plaque stabilizers. Co-administer agents that stabilize plaques and reduce the risk of rupture while the plaque is being dissolved. Anti-inflammatory drugs. Use anti-inflammatory drugs to reduce the risk of inflammation and subsequent plaque instability during treatment. 4. Monitoring and imaging. Advanced imaging techniques. Utilize imaging technologies such as intravascular ultrasound, IVUS, or optical coherence tomography, OCT, to monitor plaque stability and treatment progress in real time. Biomarkers. Develop and use biomarkers to monitor the risk of plaque rupture and inflammatory responses during treatment. 5. Combination therapy. Statins. Combine the new drug with statins, which are known to stabilize plaques and reduce inflammation. Antithrombotics. Use antithrombotic drugs to prevent the formation of blood clots in case of minor plaque dislodgement. Research and development considerations. Preclinical testing. Conduct thorough preclinical studies in animal models to assess the risk of plaque dislodgement and optimize the drug safety profile. Clinical trials. Design clinical trials with robust monitoring protocols to detect and manage any instances of plaque dislodgement or related complications early. Risk-benefit analysis. Perform a detailed risk-benefit analysis to weigh the potential advantages of the treatment against the risks of plaque dislodgement. Next steps. 1. Literature review. Review existing studies on plaque stability, enzymatic plaque degradation, and targeted drug delivery systems. 2. Expert consultation. Collaborate with experts in cardiology, pharmacology, and biomedical engineering to refine the approach and develop safety protocols. 3. Prototype development. Develop and test prototype drugs and delivery systems in vitro and in animal models. 4. Regulatory strategy. Engage with regulatory bodies early to ensure that the development pathway addresses all safety concerns and complies with regulatory standards. By addressing these risks with targeted strategies and thorough research, it is possible to develop a safer approach to treating atherosclerotic plaques. If you need help finding specific research articles or further assistance in any of these steps, please let me know. The concept of installing a net or filter upstream in the arteries to catch dislodged plaque fragments is an interesting idea and has parallels with certain medical devices used in specific contexts. However, the feasibility and safety of such an approach for general use in the arteries, particularly for the purpose of preventing complications from a plaque dissolving drug, require careful consideration. Here are some key points to consider. TAF existing technologies and applications. Embolic protection devices, EPDs, used in procedures. EPDs are already used in certain medical procedures, such as carotid artery stenting, to capture and remove debris that may dislodge during the intervention. Mechanism. These devices typically consist of small, mesh like filters that are temporarily deployed to catch debris and then removed after the procedure. 2. Inferior vena cava IVC filters. Thrombosis prevention. IVC filters are used to prevent pulmonary embolism by trapping blood clots that travel from the lower extremities to the lungs. Temporary or permanent. Some IVC filters are designed to be temporary and can be removed after the risk period has passed, while others are permanent. Feasibility and safety considerations. 1. Anatomical challenges. Arterial size and flow. The arteries, especially coronary arteries, are smaller and have higher pressure compared to veins. Designing a filter that can function effectively in this environment without causing obstruction or damage is challenging. Access and placement. Placing such a device would require minimally invasive procedures, likely using catheters. Ensuring accurate placement and secure positioning is critical. 2. Potential complications. Thrombosis. There is a risk that the net itself could become a site for thrombosis, clot formation, potentially causing further blockages. Embolization. If the filter becomes dislodged, it could travel through the bloodstream and cause embolism. Tissue damage. The device could potentially damage the arterial walls or cause irritation and inflammation. 3. Material and design. Biocompatibility. The materials used for the net must be biocompatible to prevent adverse reactions. Mesh size. The mesh size must be fine enough to capture plaque fragments, but not so fine that it impedes normal blood flow. 4. Temporal use. Temporary deployment. A temporary filter that is deployed only during the plaque dissolving treatment and then removed might reduce some risks compared to a permanent implant. Monitoring. Continuous monitoring during the treatment period would be necessary to ensure the filter is functioning correctly and to address any complications promptly. Research and Development Pathway 1. Prototype Development. Design. Develop prototypes of arterial filters with various mesh sizes and materials to test in laboratory settings. Simulation. Use computational models to simulate blood flow and the behavior of the filter in different arterial conditions.
Yeah, actually, I'm stopping it here because sounds like they've already developed that. So just use one that's already been developed, I'd say. So. It sounds like they already, yeah, just use the EPDs. So, so yeah, I'm asking about if the body would just eliminate it or basically would cause more problems. Oh boy. Okay, now I think it's ready.
The idea of liquefying heart plaque as a treatment for atherosclerosis raises the question of how the body would handle and eliminate the dissolved components. Understanding this process involves several biological mechanisms: composition and breakdown of atherosclerotic plaque, Atherosclerotic plaques are composed of lipids, fats, cholesterol, and triglycerides, fibrous tissue, collagen and elastin, calcium, deposits that can harden the plaque, cellular debris, dead cells and inflammatory cells such as macrophages. Liquefying plaque would require breaking down these components into smaller, more manageable molecules. Potential mechanisms for natural elimination. 1. Metabolism and clearance of lipids. Liver processing. Free fatty acids and cholesterol can be transported to the liver where they are metabolized. The liver can convert these lipids into bile acids, which are then excreted in the bile and eliminated through the digestive tract. Transport proteins. High density lipoproteins, HDL, can help transport cholesterol from the bloodstream and tissues to the liver for processing and excretion. 2. Breakdown and removal of proteins and cellular debris. Phagocytosis. Macrophages and other immune cells can engulf and digest cellular debris and protein fragments. These cells then process and present the degraded material for further clearance by the body's waste management systems. Proteolysis. Proteases and other enzymes break down proteins into amino acids, which can be reused by the body or excreted. 3. Calcium removal. Dissolution and excretion. Calcium can be dissolved and excreted through the kidneys in the urine. However, the efficiency of this process may vary depending on the form and amount of calcium present. Challenges and considerations. 1. Efficiency of clearance. The body's natural clearance mechanisms might not be fast or efficient enough to handle large amounts of liquefied plaque, potentially leading to an accumulation of breakdown products. 2. Systemic effects. Introducing large quantities of lipids and other breakdown products into the bloodstream could overwhelm normal metabolic pathways and lead to systemic issues such as increased lipid levels, inflammation, or kidney overload. 3. Localized treatment. Ideally, the treatment should ensure that the plaque is broken down gradually and in a controlled manner to prevent overwhelming the body's natural clearance systems. 4. Toxicity and side effects. Breakdown products must be non toxic and manageable by the body's normal metabolic and excretory processes. Research and development pathway. 1. In vitro studies. Simulation. Study the breakdown of plaque components in vitro using enzymes or chemical agents to understand the products formed and their potential impact on the body. Cellular models. Use liver and kidney cell cultures to study how these cells process and eliminate the breakdown products. 2. Animal studies. Metabolic tracking. Administer plaque dissolving agents to animal models of atherosclerosis and track the metabolic fate of the breakdown products. Organ function. Monitor liver and kidney function to assess the safety and efficiency of the clearance mechanisms. 3. Clinical trials. Safety and efficacy. Conduct clinical trials to evaluate the safety and efficacy of the treatment in humans, focusing on how well the body can handle and eliminate the breakdown products. Biomarkers. Identify biomarkers for efficient monitoring of metabolic and excretory functions during treatment. Conclusion. While the body has natural mechanisms to eliminate various metabolic byproducts, the feasibility and safety of liquefying heart plaque and relying on these mechanisms for elimination require thorough investigation. Controlled and gradual breakdown of plaque, combined with monitoring and support for the body's clearance systems, could potentially make this approach viable. Further research is necessary to understand the precise metabolic pathways and potential bottlenecks in this process. If you need assistance finding specific research articles or developing a detailed experimental plan, please let me know.
Oh man, that's so cool. So yeah, that's cool. It actually did cover the like. I was thinking as I was talking about that maybe something that does that gradually would make it more feasible because the body probably could eliminate that better versus shocking the body with all sorts of heart plaque at once, dissolved heart plaque at once. Yeah, that's pretty cool. Feel free to share this with your researcher friends if you have any, or if you're a researcher yourself, feel free to use it. Mm. definitely like to hear feedback on this. Feel free to comment below in the video if you have any comments on it. Thank you for watching. Feel free to like and subscribe. Have a good day. I hope this really helps some people here.